Atif, can you see the screen? Hello, Atif, can you see the screen? No. इनका तो नेट ठीक नहीं रहता है, पता नहीं.
Yes, sir.
Why am I not audible properly? What happened?
No, sir, it's gone for a while, sir. Yes, sir, you're audible.
Okay. I was asking whether the screen is. Can you see the screen? Yes or no?
Yes, sir, you can see this.
Okay. Fine. Now, in P block elements, first thing is that it has metals. Wait a second. It has, first of all, let me write non-metals. Metalloids and metals. Okay. It has non-metals, metalloids, and also metals. Now, when you look at the NCERT textbook, so what it has done, it has, you first of all, okay, let me write one thing. You have to remember metalloids. Remember the metalloids of each group. Okay. Now, all atoms above metalloids in the group are non-metals, and all atoms below metalloids are metals. Okay.
Yes, sir.
Okay. So first of all, what are the metalloids? What are the metalloids? Now, here you will see a bit of what I can say is difference of opinion in the metalloid. But again, you have to look at the NCERT, what it is saying. Okay, NCERT, what it is saying. So when you look at the NCERT and in the P block elements, in the group 13, let us start with the group 13 here. Now the group 13, boron is supposed to be a metalloid. It is supposed to be a metalloid, but NCERT, it doesn't represent boron as a metalloid. Okay, so you have to keep only aluminium as a metalloid there. Okay, only aluminium as a metalloid. Last time I checked, I don't think there is any new edition of NCERT where they have changed anything. I think so. Yes, it is still the same thing. So you can write here. So one thing is that you have to identify metalloid in all of them. Then in general, you can write oxides of non-metal. They will be either acidic or neutral, or acidic, or they will be neutral. Oxides of metalloid. Oxides of metalloid, they will be amphoteric. And oxides of metals are basic in nature. They will be basic in nature. Okay. Now, let us now look at the one important property, that is inert pair effect. For that, let me just borrow something from the internet. That is the electronic configuration of the elements, group 13. Electronic configuration. Yeah. Let us look at the valence electrons here. Okay. The outermost, let us say the outermost electron, let us see. So the outermost electron here will be 2p1, 3p1, 4p1, 6p1, and you can also say 6s2, 6p1 is there, 5s2, 4s2, 3s2, and 2s2. Yes or no? Correct. These are the outermost electrons. Khalil, are you there? Oh, sorry, Atif, are you there?
Sir, you called me? So can you hear me?
Are you not here? What happened? No, I'm
Nothing
asking, are you
happened,
not
sir.
present? Huh?
Yes, sir. I said I'm present. I'm present.
Okay. So I asked you something. So can you tell me, by looking at the electronic configuration, what is the valency of group 13 elements?
Yes, sir.
What is it?
1.
Look again.
Oh, 3, sir. 3.
It is 3. Okay. Now let's also look at the shielding. Okay. So we can see that before 2s2 we have the helium atom. So helium atom, it is having 1s2 configuration. Okay, 1s2 configuration. Now as I go down from boron to aluminium, now when I go from aluminium to gallium, you can see there is a 3D shell here. There is a 3D subshell here, right? Yes or no?
Yes, sir.
Now, when we are talking about the boron, the shielding was done by S. When we are talking about neon, sorry, when we are talking about aluminium, the shielding was done by S and P, right? Most probably P. And when we talk about gallium, the shielding is done by D subshell. Yes or no? Correct?
Yes, sir.
Now, we also know that the shielding is S block. They have most effective shielding, followed by P, followed by D, and then followed by F, right? Followed by F. So the most effective is S, then P, then D, and F. And that is why you can say that in gallium, indium, and thallium, as we go down the group, shielding decreases. Yes or no? Shielding decreases, correct?
Yes.
Now, if shielding is decreasing, what is going to happen? The valence electron are under attraction of nucleus. The nucleus is going to attract the electrons more effectively. Correct. Now, when it is attracting more effectively, it results in quite inertness of a few electrons. What happens is that as I go down the group, I can say that generally the valency is what? The valency of group 13 is 3. The valency is 3. But as I go down, what happens? These S subshell electrons, these are very effective. Now, this S is what? Very near to the nucleus. And also the shielding is not effective. That means the nucleus, it is attracting this S subshell very effectively, and the nucleus doesn't let this S subshell to participate in bond formation. Why? Due to the low shielding, the effective nuclear charge is high. The S subshell are under the control of nucleus, and the nucleus is not letting the S subshell to go away and take part in bond formation. And that is why we see one other valency, that is of 1. So 3 and 1 are the two valencies of the group 13 element. And also it will be, if I talk about the oxidation state, it will be +3 and +1. Okay, +3 and +1. They will be giving electrons. Okay. Next thing is that what is going to happen to the valence oxidation state? So as I go down, let me write a topic which is known as the inert pair effect. It is the reluctance of S subshell, or reluctance of electrons in S subshell to take part in bond formation. Okay, so this is very important. Inert pair effect. They can ask you directly what is inert pair effect. That is the reluctance of electrons in the S subshell to take part in bond formation. Now, if I talk about the oxidation state of group 13, there are two oxidation states. One is +3 and the other is +1. So the stability of +3 decreases down the group. +1 is stability of +1 oxidation state increases down the group. Due to inert pair effect. Okay. So tell me if you understand these 2 points, yes or no?
Yes, sir.
Okay. Now, due to this inert pair effect, and also due to this low shielding, there are many anomalies that you will get. There are many anomalies that you are getting in the group 13 elements. So the first is the atomic size. First is the atomic size of these elements. Okay. So when I look at the atomic size, generally expected order will be boron will have the smallest, aluminium, gallium, then indium, and then thallium. Okay, so this is the expected order. Now, when I look at the actual order is we have boron, that is true. But after boron, the atomic size of aluminium, it is what? It is greater than gallium. So after boron, we have gallium. And after gallium, we have aluminium. Then it is followed by indium and thallium. Then thallium. Okay, so these are very similar. Indium and thallium, this is 167 picometer, this is 170 picometer. Gallium is 135, and I think this is 143 picometer. Okay, so you can see that indium and thallium also has, this is very less difference. Okay, and here also we have, here the order is only reversed, right? We should have aluminium, it should be smaller than gallium, but gallium is smaller than aluminium. What is the explanation? So explanation number one for gallium and aluminium. Okay, that is the introduction of d orbital electrons in gallium reduces the shielding drastically, and hence the nucleus attracts electrons effectively, making the size of atom small. Okay, this is for gallium and aluminium. Secondly, the difference, that means in indium and thallium, we expected that they should be what, very different, but it is like very small differences there. It is, you can say it is indium and thallium are almost equal. So for indium and thallium, the reason is going to be the same, but there will be introduction of f orbital electrons in thallium. Okay, and so on. Reduces the shielding drastically, and hence the nucleus attract electron effectively, making the size of atom small. As you can see here, there are f electrons in the thallium atom, but not in the indium atom. Okay, so these are the two explanations for the atomic size. Is this clear? Yes or no?
Yes, sir.
Okay. Now let's talk about the ionization enthalpy. Ionization enthalpy. Okay. Number 1 point. So one thing is for sure, I know, I hope you know that first ionization enthalpy of the group 13 elements are less than the corresponding members of alkaline earth metals. That means group 2 elements. So first ionization enthalpy of group 13 is less than group 2 due to the outermost electron in group 13 is in p block, in the p subshell, sorry, in the p block, in the p subshell, and that is why it is easier to remove electron from the group 13 elements rather from the group 2 elements. Okay, but if I look in the group itself, then if I move down from boron to aluminium, so again I can write some expected order here. Expected order of the first ionization enthalpy will be, for first ionization enthalpy, it is okay. The boron will have the highest, followed by aluminium, followed by gallium, followed by indium, and then followed by thallium, right? Because boron is going to be small, so removing electrons from boron will be more difficult because the electron, it is nearer to the nucleus, and that is why we need to input more energy, and that is why the ionization enthalpy would be higher for boron than for aluminium, gallium, indium, and thallium. Is that right? Yes or no? Do you understand this?
Yes.
Okay. Now, the first ionization enthalpy that we see, the actual is actual order that we see, that yeah, that is right, that boron is having a higher ionization enthalpy than aluminium. But when I look at aluminium and gallium and indium, so after the boron atom, next we have an order that is thallium. And after that, I think there is gallium, and then we have aluminium. And after that, we have indium. Okay, this is around 800. For thallium, it is around 600, I think, or 590. For gallium, it is 580. Aluminium also, it is somewhere around 580, 575, I think. And for indium, it is the lowest. I think it is around 550 or something kilojoule per mole. Okay, so you can see 800, then 590 is thallium, followed by 580, 575, and 540. So why is thallium very less? Again, so the thallium, it is the ionization enthalpy is what? Ionization enthalpy is 590 here. Why? Because it is a metal. Okay, so removal of one electron okay, so let me write again here. So for thallium, it is what? Thallium is 590, which is very higher. So why it is? Due to introduction of F subshell electrons. Okay, due to F subshell electron, this is the answer you are going to give. Okay, for gallium and aluminium, when we are comparing these two, so introduction of D subshell electrons. Okay, introduction of D subshell electrons. This is the reason that you are going to give. Okay, so tell me, is this clear? Yes or no? So mainly the reason whatever you are going to see here is due to the shielding. Okay, so the shielding decreases. That is the most important point in this group 13 elements, that the shielding is drastically decreasing if I go from aluminium to gallium and indium to thallium, and that is represented in all of the properties that we are seeing right now. Tell me, is this clear? Yes or no? Yes. Yes, Atif, is this clear? What happened, Atif?
Some technical issues there.
Okay, so just write like only one or two more things is there. So we have discussed the oxidation states, and let us also discuss the basic character of oxides and hydroxides. Basic character of oxides and hydroxides. So first thing is that the basic character of both oxides and hydroxides, they will increase as we go down the group. So basic character, it increases as we go down the group. Okay, as we go down the group. So if I talk about the oxides, we have B2O3, we have Al2O3 and Ga2O3. Then for indium, it will be In2O3 and Tl2O3. For hydroxides, we will have BOH whole thrice, AlOH whole thrice, GaOH whole thrice, InOH whole thrice, TlOH whole thrice. So in this, it will increase, obviously. That is one thing for sure, that the basic character increases as we go down the group. Okay, but this is acidic in nature. For gallium and aluminium, these are amphoteric. And indium and thallium, these are basic in nature. Okay, these are basic in nature. These are the three things that we have to see. Now, what is the explanation here? What is the explanation? Because as we move down the group, what is going to happen? The magnitude of ionization energy is decreasing. And as a result, the strength of this MO bond, whatever the metal, whatever the element is there, for example, boron and aluminium and so on, the MO bond, it decreases. We have boron and oxygen bond, so this bond will be very strong. But if I talk about indium and oxygen, or in thallium and oxygen bond, these are going to be weak bonds. So that means the breaking of these bonds are easy, and that is why the basic character increases. The basic character increases. Explanation would be as we go down the group, the MO bond strength decreases. Okay, next that is important, which is the back bonding concept. Back bonding in halides. So all halides have formula. Atom of group 13A and X3. X3 will be any halogen atom. So AX3 has 3 bonds. That is 6 electron in valence shell, and hence octet is incomplete, and AX3 is electron deficient. AX3 is electron deficient. Okay. Now the next thing is, since the AX3 is electron deficient, AX3 act as Lewis acid, which these are electron pair acceptors. Okay, Lewis acids are electron pair acceptors. Now, when I talk about the stability of, different types of halides of boron, so it depends on 2 things. First of all, we have to look at a particular the halides of the group 13 element. That means BX3, and then we have BX3. What else do we have? We have BX3. AlX3 will be there. For gallium will be there. For indium will be there. Then for thallium will be there. We have to look at the stability of these molecules. I have BX3, ALX3, GAX3, indium X3, and thallium X3. Okay, thallium X3. Now, in this case, you can see that it is solely dependent on what is same. X3 is same here, but boron, aluminium, gallium, indium, and thallium, these are different. These are different here. Okay, these are different. So it will depend on the group 13 elements. It will depend on the group 13 elements. So what do you think? Atif, tell me, which will be more stable? Here we have 3 positive. This is 3 positive. This is 3 positive, and this is 3 positive, and this is 3 positive. Now, when I look at the oxidation state, then I can obviously say that B, which has 3 positive, will be more stable than aluminium, then gallium, and then indium, and then thallium. Why? Because we have said that stability of +3 decreases down the group. Okay, since the stability of +3 decreases down the group, so boron X3 will be most stable, followed by AlX3, followed by gallium, indium, and thallium. Next is the stability of boron halide. Stability of boron halide. So we have BF3, BCl3, BBr3, and we have BI3. Okay, so the expected order was that BI3 will be more stable because it is least electronegative, and the boron will be having most of the electrons. And since BF3, we had this order here. Why? Due to high electronegativity. Due to high electronegativity, fluorine will make boron more electron deficient. But the actual order is just reverse. BF3 is most stable, followed by BCl3, followed by BBr3, followed by BI3. The reason for this stability of BF3 is, back bonding. So in BF3, if I look here, so boron is like this. There are fluorine atoms. All the fluorine atoms have lone pair electrons. And the boron, it has a vacant p orbital. Now, all of these fluorine atoms, they have a capability of giving the lone pair electrons to the boron atom, to the boron vacant p orbital. Okay. Now, this type of back bonding is available in all of them. This is known as back bonding. This is known as what? Back bonding. So electrons, whenever you have electrons and there is some vacant orbital, the electrons will move there. Okay. It is the constant rule. Electrons go from a electron rich source to the electron poor source. So electron rich is fluorine, electron poor is boron. So electron just moves there. It finds a vacant orbital, it will go there. So this is known as back bonding. Fluorine is donating electrons. Now this type of back bonding is available in all of these. This of the back bonding. So there will be back bonding between, okay, boron and fluorine. There can be back bonding between Cl and boron also, fluorine and boron. There can be back bonding between BBr also, bromine and boron. There can be between iodine and boron also. But if I look at the back bonding here, I can say that fluorine is in the second period element. Boron is also second period. This is third period to second period. This is fourth period, second period, and this is fifth period and second period. And that is why the BF back bonding will be more effective, followed by BCl, followed by BBr, and then followed by BI3. Here you will write, since BF back bonding is between 2p orbitals, between 2p orbitals, it is the most strong back bonding which stabilizes the boron atom. Stabilizes the boron atom. Okay. Right. So these are the main things. Okay, these are the main things till here, and the rest of the part when we will be doing revisions, I will be. You have to read the NCERT, and we will be discussing the questions. Okay, then we will be discussing the question. These are the explanatory points. The main explanation was the shielding effect. Okay, so the shielding effect is the driving property of all the chemical, the driving parameter for all the properties, I can say. And shielding leads to inert pair effect, and all the reasons that you see in NCERT, they will be given in terms of inert pair effect. So we'll be writing about inert pair effect and about the shielding whenever you are asked about, let us say, why is the stability of +1 increasing as we go down the group. So inert pair effect. Why is the atomic size different? Due to shielding. Why is the ionization enthalpy having some anomaly? Due to shielding again. Okay, due to shielding. Okay, so these are the things that you have to remember. And yeah, then back bonding is something that you have to remember. Okay, back bonding is something that you have to remember. Then if you look at the carbon family, it has not much anomaly. You can read it and then you will understand it if you know something about the inert pair effect.